Welcome to Lesson 1, Kinetic Molecular Theory, Ideal versus Real Gases. Our lesson objectives: differentiate between ideal and real gases and compare the entropy of solids, liquids, and gases. Scientists construct models to help explain things around them. So, for example, the behavior of substances. And so a study of these behavior of gases has led to this model that scientists constructed called the Kinetic Molecular Theory of Gases, or the KMT for short. And this model describes the relationships among pressure, volume, temperature, velocity, frequency, and the force of collisions between gas particles. And for this model to hold true, some assumptions about gases had to be made. And so they had to assume that gases are composed of a large number of particles that are in this constant random, we say, straight line motion until they collide with each other or the walls of the container. So looking at this model here, you can see these are the straight line motion, but it's very random. The second assumption is that the volume of gas is negligible, meaning zero. This is because if you look at the distance between the particles are so great, there's so much empty space, that in comparison to the very small gas particles, we can say that the particle's volume is essentially negligible. The third assumption is that there's no force of attraction between the gas particles or with the walls of the container. And the last one is that collisions between gas particles or with the walls of the container are perfectly elastic. That means that no energy is lost during a collision. So as you see here, an example of these billiard balls here, when the billiard balls hit, there is no loss of energy, and that is just transferred from one ball to the next, and the balls continue to move. But I want you to remember, these are models. And so the kinetic theory of gases is a theoretical model. And so it's describing what we say an ideal behavior of a gas is. Real gases in real life do not behave exactly like the ideal gas in this theoretical model. And so in real gases, the following two factors contribute to deviations from the ideal model. The first one is that real gases do have a small amount of volume, and it is significant. And the second factor is that gas particles do have some attractive force on each other. And so then, how do we get our real gas to behave most like an ideal gas? So going back here, how do we get our real gas to have the least amount of volume of particles and the least attractive force on each other? If we take our real gases and we put them in a condition of high temperature and low pressure, they're going to behave most like this ideal model. Here's why. Under high temperature, we have a lot of kinetic energy, and therefore the particles are moving faster. If they're moving faster, it's much harder for them to attract each other. Under low pressure, the particles are further away from each other. Again, if they're further away from each other, just like when they're moving fast, it's harder for them to attract each other. So these two conditions make it much more challenging for the gas particles to attract each other, and that satisfies that assumption that gas particles have no attractive forces. So let's see that here. Low temperature versus high temperature. So as you see, under conditions of high temperature, they're moving much faster than low temperature. And so it's much harder for these particles then to attract each other if they're moving so fast. Because remember, the attractive force would have to overcome the kinetic energy. And the kinetic energy is so great, it can't do that. In terms of pressure, under high pressure, you see the particles are close together. It's easy to attract each other. Under low pressure, see how much more they're spread out. And so low pressure means they're further away, means the attractive forces are lower. And so the way to remember these conditions, these ideal conditions, is the acronym PLIGHT. We want the pressure low for an ideal gas, and we want high temperature. Conversely, gases will be least like an ideal gas, or we say they deviate or stray from the ideal conditions under the opposite, under low temperature and high pressure. Because if the temperature is low, they're moving slower, which means it's easier for them to attract each other. And the same thing under high pressure, they're closer together. Again, it's easier for them to attract each other. So here's a summary of the ideal gas conditions versus the real gases. And so again, PLIGHT, pressure low, high temperature, tells us how do we get these real gases to behave most like an ideal gas. So here's an example we would see of a question pertaining to this topic. Under which conditions of temperature and pressure would helium behave most like an ideal gas? So that's our PLIGHT. We want the pressure low and we want the high temperature. So high temperature would be either choice C or D. This is much higher than 50. And then we want the low pressure. So 20 kilopascals is much lower than 600 kilopascals. And so choice C would be our answer. High temperature, low pressure. Least attraction between the gas particles. Now, as these particles are moving around, they're hitting the sides of the container, whatever it may be. So in this case, it happens to be a balloon. And so when they hit the container, they're applying force to the container, or in this case, the balloon itself. And so that force is called gas pressure. And we measure that in this class with either kilopascals or ATM, which is atmospheres. And so the relationship between these two is on table A, where we have 1 atmosphere equals 101.3 kilopascals. So if I had 2 atmospheres, it would be 2 times that. What are the factors that affect gas pressure? Well, first is the amount of gas, how many moles of gas I have. If I add more gas particles, I'm going to have a higher pressure. Increasing the amount will increase that pressure, and obviously then the opposite. If I decrease the amount of gas particles, the pressure will decrease. And that's the case with our tires. When we fill up our tires, we're adding more gas in there, and so therefore we're increasing the pressure, and that's why the tire pressure goes up. Temperature. If we increase temperature, pressure goes up. If we decrease temperature, pressure goes down. And we can see this on a cold day, much like what's going on in the winter right now. If the temperature is colder, we see that our gas pressure will decrease, and maybe your pressure light will go on in your car. And lastly, volume. Decreasing volume will increase pressure. So when I squeeze a balloon, I decrease the volume, pressure goes up, and sometimes the balloon will pop. And then obviously conversely, if I increase the volume, the pressure is going to go down. So let's check your understanding. Can you differentiate between ideal and real gases? The last thing I want to talk about is something called entropy. Entropy is a measure of the number of different possible arrangement of atoms. We call these things microstates. How many different ways can I arrange something? And so entropy is going to increase with increasing disorder of particles. The more particles I have, or the more places they can be, the more different arrangements I have, and therefore the increase in entropy. For example, if I have 4 different particles, how many different ways can I arrange them? Well, if I have 2 places they could be, I can arrange them in all these different possible combinations, or all these different microstates. And so the more particles I have, the more arrangements I would have, and the more boxes I have, the more arrangements I could have. So when we compare states of matter, if you look at solid versus liquid versus gas, if you look at the entropy, solid, since they're all kind of put together, there's only a few different arrangements I could have in this solid form. As I go to a liquid, since they're more spread out, now there's more possible arrangements or microstates I could have, so entropy starts to increase. So this disorder, this messiness, starts to increase. And then if you look at a gas, they're even more spread out, so there's more possible ways I could have these particles arranged in this space, and so the entropy is really high. So entropy increases from solid to liquid to gas. And if you look at all the other things we've learned this year, particle arrangement, intermolecular forces, shape, and volume, these are all things we've learned throughout the course so far. So solids, they are very ordered, close together, and they're vibrating in place. Liquids, less ordered, meaning more entropy, and we can flow around each other. And then obviously in gases, they are the furthest apart. And so what's holding solids together? Higher attractive forces, and then gases have the least attractive forces, therefore they are spread out the most. So let's check your understanding. Can you compare the entropy of solids, liquids, and gases? At this point, you should be able to differentiate between ideal and real gases and compare the entropy of solids, liquids, and gases.